very much. It's a great pleasure to be here, and it's a great pleasure to be able to give you be given the freedom to give quite a long talk, so I can go into the details, which I kind of enjoy from time to time. So I was given the topic of atmospheric escape, no other qualifiers after that, but I've simplified it slightly to atmospheric escape of highly irradiated exoplanets, and there's a good reason for that, which I'll show you in a second. And I've also simplified it further that I'm just going to focus on atmospheric escape that's thermally driven, so driven by heating rather than any other processes. So the reason why I think we should be thinking about atmospheric escape for highly irradiated planets is when we look at the kind of exoplanets that we're going to be able to probe over the coming decade, they are dominated by two facts. So these are test yields. They're small planets, all less than 4 Earth radii. You can go to this catalog. This also includes some sort of estimation of what the TESS extended mission will do. So now we're in the era that TESS has sort of finished its first year of operations, it's into its second year of operations, and now it's going into the extended mission. You find two things when you go through these yields. Firstly, that the majority of the planets that we're going to find are billions of years old, but they're also incredibly highly irradiated. Right? So this is Earth down here, this is Mercury in our solar system, and this is where the majority of the exoplanets we're going to discover and be able to characterize in the next decade sit. So they're sort of at a radiation level that's 100 times or 30 times bigger than the Earth, and at least an order of magnitude larger than Mercury. This is even more pronounced when you look at the small planets. So the small planets are going to, again, be dominated by being these highly irradiated planets. Now, this is important because irradiation drives escape. And the fact they're also old also has another consequence. Given that escape tends to be driven by the X-rays and the EUV that the star outputs, which is much, much larger in the star's youth than when we see these today, this means that for all the small exoplanets that we're probably going to get spectra of for the next 10 years, atmospheric escape will have already sculpted their atmospheres. So this is a process that we're going to need to understand in order to understand the compositions and the properties of the atmospheres that we're going to be detecting over the next 10 years. And there's lots of work to do, especially as we move towards the terrestrial planets. This problem is sort of somewhat unsolved. So in this talk, I'm going to go through a few things. I'm going to talk about the very basic physics of thermal escape. What do I mean? What are the different regimes that you might think about? I'm going to then talk about sort of hydrogen helium dominated atmospheres. And this is where in the exoplanet community, we sort of focused our theoretical work over the last 10 years, and we've had quite a bit of a success. Then I'm going to talk about water loss from habitable zone planets around M-dwarfs. This is a very important problem if we want to start thinking about habitability of M-dwarfs, is that they have, due to their stellar evolution, they have quite a different track to temperate planets around sun-like stars. If I get time, I'm going to allude to perhaps a pathway to how we can understand atmospheric escape from more complicated heavy element or secondary atmospheres. And that's with sort of my favorite topic at the moment, which is sort of silicate vapor atmospheres around ultra short period planets. These are planets that are so close to the star is actually able to melt their rocky surface and form a silicate vapor atmosphere. And throughout this talk, I'm going to sort of also point to the problems that we need to, theoretical problems that we need to address over the next 10 years or so. So the physics of thermally driven escape. So I said in this talk, I'm going to only focus on thermally driven escape driven by heating. There is a poster which is on impact-driven escape, which I encourage you to go look at as well. So thermally driven escape, in its most simple keynote cartoon version, is that the star is heating outputting some photons, and it heats the planet's atmosphere. It heats the surface layers of the planet's atmosphere, and that atmosphere becomes hot enough that it can escape from the planet. In more detail, there are a couple of limits of this process. So if you consider the planet's atmosphere, which I've shown here, these are atoms in the planet's atmosphere. The base of the planet's down here, and the top of the atmosphere is up here. So under the stratification of gravity, the density is much, much lower, close to the surface of the planet. And the density of the gas is much, much higher, lower, close to the surface of the planet, but it's much, much lower at higher altitudes. And our photons from our star come in and they heat. And in order to understand what regimes you are in for thermal escape, there's two sort of critical radii in this atmosphere. So there's where the particle mean free path equals the atmospheric scale height. So this is the distance the particles travel before they collide with another gas particle. If you reach the point where the mean free path of the particles is larger than the planet's scale height, then the atoms in the atmosphere are essentially sort of going up and down, never colliding with another atom. So they're behaving in a sort of collisionless way. Below this limit, where the density is high enough, the mean free path is shorter than the scale height, the gas behaves more like a fluid. It's a collisionless process. There's another critical density, or critical radius in the atmosphere, is where the particle's thermal energy exceeds their binding energy, their gravitational binding energy. So if you're above this radius, you would have enough thermal energy to escape from the planet's gravity. And the thermal escape regime you end up sitting in depends on which of these radii you encounter first as you go up in the atmosphere. So if we think about a weakly irradiated atmosphere first, it's not very hot. It's not very hot. Then you need to go high up into the atmosphere before you have sufficient thermal energy to be unbound from the planet's gravity. So the point at which the particle thermal energy exceeds the gravitational potential energy is very, very high up in the atmosphere. And it's higher compared to where the particle mean free path is approximately equal to the scale height. This also has another name, it's the exobase. Now, this has a consequence for how you might escape, because as I said earlier, still getting used to this pointer, any of the particles that are above this exobase line here, where the particle free path is bigger than the scale height, basically don't collide with another atom. They behave almost in a collisionless manner. So if you envisage that you have some sort of velocity or energy distribution for those particles, any particle that gains sufficient kinetic energy that it's no longer bound to the planet's gravity can just freely escape into space. So you sort of lose this tail of this distribution here. So if this was a Maxwell-Boltzmann distribution, then this would be sort of you'd be out in the exponential tail of the Maxwell-Boltzmann distribution. So this tells you, because you're out in this Maxwell-Boltzmann distribution and its exponential function, this is not a very, very efficient process. It's not a very quick process of losing your atmosphere. So this is the kind of atmospheric escape that's driving some losses from the Earth today. And the mass loss rate from the Earth's atmosphere is very, very long. It is longer than sort of one Earth atmosphere per sort of 100 billion years, which is pretty good for habitability. We're not going to lose our atmosphere in the next few years, which is good. We might ruin it in the next few years, but we're not going to lose it. But there's an opposite limit, which is when you become strongly irradiated and you switch where those two heights appear in your atmosphere. So now you have your where your particle thermal energy exceeds your gravitational potential deep in your atmosphere compared to where your exobase is, which is much, much higher. And now you have sufficient thermal energy to escape the planet's gravitational well, and what you do is you drive a hydrodynamic wind. So you drive a pressure-driven wind that escapes from the planet's gravity. And instead of losing just this sort of exponential tail of your Maxwell-Boltzmann distribution of your gas particles, you lose the bulk now. And this is a much more efficient process. So once you're in the hydrodynamic regime, or once you're in this strongly irradiated regime, atmospheric escape and hydrodynamic escape is a very, very efficient process. And it can dramatically alter your atmosphere over the billions of years that a planet has to evolve. So in a little more detail, this is now instead a slice through one of those large simulations, just showing the temperature structure as a function of altitude and the velocity structure as a function of altitude. So this is for a typical highly irradiated hydrogen helium dominated atmosphere that's at about sort of 0.1 AU from its star. The UV and the X-rays heat the upper atmospheres to about 10 to the 4 Kelvin. And this is sufficient to drive this very powerful hydrodynamic outflow. And one of the critical things that also happens in this process is the gas starts off subsonic and then it becomes supersonic at large radius. And once the gas is supersonic, there's no way for anything that happens out here to tell the planet's atmosphere about what's going on. You can only propagate information at the sound speed. So if you're traveling faster than the sound speed, any information you try and send backwards is just going to be advected out with you. So anything that happens outside this sonic point here which also turns out to be exactly roughly where the thermal energy exceeds the gravitational potential energy, is not going to affect your outflow. So you can do basically whatever you want outside here, and it's not going to affect what happens. So you can put your exobase up here, you can become collisionless, your equations of hydrodynamics no longer apply, the flow doesn't care. You still get this hydrodynamic escape. However, if you push your exobase down, we're back in the gene's escape limit. Even though I've solved the problem, assuming the equations of hydrodynamics apply, this is not applicable. So I have to go to the gene's escape limit. So you can think of the transition from hydrodynamic escape to gene's escape being roughly when the exobase is at the sonic point of these outflows. And that's a good way to think about it. And that's how we actually calculate this transition in numerical simulations. So in reality, one would want to solve the collisional Boltzmann equation that goes straight from the hydrodynamic limit all the way to the non-hydrodynamic collisionless limit. That is computationally impossible. So what we typically do is we solve the equations of hydrodynamics. We check that you're in the hydrodynamic limit through this criterion, and if you're not, then you switch to the gene's escape limit. So a little more going into the details. So this is our planet's atmosphere here. This is atmosphere surrounding surface of a planet, and we have two heating sources in these cases. The first heating source is photons from the star, and a second heating source, especially if you have a big atmosphere or at young ages, is thermal heating from the interior. And this gives you sort of a layered structure as to the heating profile. So in hydrogen helium dominated atmospheres, first you absorb the EUV photons, then you absorb the X-rays and the FUV driven photons. And then you have a region which is heated both bolometrically by the star and from the star's interior. And all the kind of atmospheric escape I'm going to talk about in this talk is driven basically from these layers here. But in Hilke's talk later in this session, she's going to talk about a type of mass loss that is driven by heating from the interior. And you may be aware there's a little bit of debate as to what is driving mass loss from sub-Neptunes and super-Earths. And the reason there's a little bit of debate is that this entire sort of layered structure of heating has not been properly solved in simulations. So what people like me tend to do is just sort of ignore this bit and just do this bit. And what Hilke's model is doing at the moment is just doing this part and ignoring this part. So there's a little bit of debate because these models have not been combined. And this is work in progress that needs to be done. I also want to point out that this layered structure is only necessarily true for hydrogen helium atmospheres, and I can imagine and envisage, because X-rays are preferentially absorbed by heavy elements and metals, is that if you go to secondary atmospheres, you could reverse this kind of layered structure, and this could have interesting effects for the kind of escape we get. So there is a very simple way to describe this process. It's called energy-limited escape. You may have heard of it. It's a sort of back-of-the-envelope calculation. And what you do is you say, I have some irradiation from the star, and in some unit time, my planet's area, the area the planet subtends to the star, absorbs that energy. And then it takes that energy and it uses it to unbind a fraction delta M of the atmosphere. And you go, aha, this looks magnificent. I have delta M here and delta T here. I can rearrange and I can get a mass loss rate. So I have, basically by equating the flux I'm absorbing from the star with the potential I'm escaping for, I can get an approximate expression, and I can make it an exact expression by sticking in a fudge factor. And then I can call this the efficiency. And this efficiency basically accounts for all of our ignorance. It accounts for stuff we don't or can't or need to model with simulations. So sort of radiative losses, hydrodynamic losses, and losses due to ionization, right? If you have a high energy photon, like an EUV photon come in, the way it heats is by ionizing a hydrogen atom. So an enormous amount of its energy goes into unbinding the electron from the hydrogen atom. So you can't actually use EUV photons at 100% efficiency. In fact, you only use a small fraction of an EUV photon to actually do heating. Most of it goes into ionization. So the other key point is, unsurprisingly, when you do simulations, the mass loss efficiency is not constant. This should not be a shocking result to you. And you can see that it varies. This is just one numerical calculation for one flux at one stellar age. You can see that the efficiency varies by about an order of magnitude. But if you were to sort of put a gun to my head and force me, I'd say the efficiency is about 10% for the sub-Neptunes and super-Earth and about 1% for the hot Jupiter. You can also see that it doesn't even have to scale linearly with flux. So this is a nice plot from Ruth Murray Clay showing the mass loss rate as a function of input UV flux. So at low UV fluxes, you get an almost linear scaling. This is what you would expect from this energy-limited process. But as you go to higher and higher fluxes, the scaling with mass loss rate with flux gets weaker and weaker and weaker. And this is well understood in terms of a physical process. This is where radiative recombinations kick in, and you get much lower efficiency mass loss. The other thing you note is that sort of in the strictest definition of the word, mass loss is not always energy limited. So what this energy limit really means is you take your heating and you convert it into PDV work as you're expanding from the planet's potential, and you get mass loss. This means that the sort of dominant loss mechanism that you would expect to be playing a role in this process is energy losses in PDV work. And this isn't actually true for the entire region of parameter space. But again, these are just two examples of two calculations for two fluxes, a higher flux and a lower flux. So this blue region here for EUV heating is what you would expect, roughly energy limited. So the flux in is mostly lost as PDV work. But there are other regions where this radiative recombination process dominates, where hydrogen atoms recombine. That gives you very efficient cooling. Also, the other thing you should note about the energy limited formula is the mass loss rate goes to infinity as the mass goes to zero, which also sounds a bit weird. And it is weird and it's wrong. And eventually you run out of photons. Basically, if you only have a certain number of photons, you can only ionize a certain number of hydrogen atoms, and you can only get a certain amount of mass loss. So at sort of very low gravities, you need to also take into account the number of photons that are going into the outflow, not just the energy of those photons. So it seems like perhaps energy-limited mass loss is not a bad approximation for the super-Earths and said Neptunes. But one of the other things to realize is if they truly are hydrogen and helium-dominated atmospheres, when they formed at very, very young ages, they were much, much larger. They would have sort of sat on this side of the plot. So while the energy-limited formalism is a great formalism for understanding the details of what's going on, and it's a great formalism for sort of getting an idea of how important you think atmospheric escape and how important you think mass loss is, if you really want to do sophisticated calculations, then unfortunately, like many things in modern physics, you need to go to more detailed numerical calculations. So the first part of this sort of review is I'm going to focus on kind of key results from escape from hydrogen-helium-rich, highly irradiated exoplanets. So we have these two main sources of heating from stars. We have X-ray photons and EUV photons. For hydrogen-helium-dominated atmospheres, the EUV is absorbed first. So EUV is absorbed first, and then the X-rays go a bit deeper in the atmosphere, and you drive some outflow. So as I said earlier, the key for understanding what's going on and what's doing the driving is where the sonic point sits in this outflow, because if anything goes on after the sonic point, you can't tell the planet's atmosphere about it. So you can have two different types of outflow. You can have sort of X-ray driven outflow where you get the sonic point in the X-ray driven regime and all the EUV photons are absorbed outside the sonic point. So we call this X-ray driven flow, and the EUV cannot affect the mass loss rate. So when you take that flux in the energy limited formula and you call it XUV flux for X-ray and UV, you have to sort of decide how much of the X-rays and how much of the EUV do I put into that flux. And you need to understand the structure of the outflow to decide how you do that. Obviously, you can go to the other limit now where the sonic point now sits in the EUV-driven flow and the X-rays are playing a minor role. All they're really doing is puffing up the atmosphere slightly more. So it turns out that this dominates at high fluxes and high stellar X-ray luminosities. You can sort of envisage that is because the more and more heating you kind of dump into this outflow structure, the more powerful the outflow, the faster the velocity increases. So the likelihood that you cross the sonic point in the X-ray heated regime rather than the EUV heated regime is going to be at high stellar fluxes and high luminosities. So this really means that this kind of mass loss may be important early in the planet's life. Sort of, this is perhaps what's driving the evolution that we see. But when we compare to direct observations of atmospheric escape today, it's going to be the EUV that's important. So this is something that we also have to bear in mind, that are the simulations and the models of atmospheric escape we're comparing to observed exoplanets today really applicable to what might have been going on early in the planet's lifetime? That's the complication. And also, I just want to sort of emphasize that the EUV and the X-ray flux also is not constant with time. There's actually a very nice correlation between the EUV flux and the X-ray flux as a function of the X-ray flux the star outputs. So at higher stellar X-ray fluxes, the star outputs more of its energy in the X-rays than the EUV. So this kind of enhances this idea that X-ray driven rather than EUV driven flow is going to be more important at early times. So the all-important things are what are the mass loss rates and what do they do to the planet's atmosphere? So this is sort of one example of one calculation for one age at one flux, and you can take these calculations and you can put them together and you can sort of model the evolution of planetary atmospheres over their lifetimes. So this is a calculation for a highly irradiated hot Jupiter, and it doesn't lose very much mass. And there are two reasons for this, right? I said earlier that the efficiencies for hot Jupiters are quite low, about 1%. But also hot Jupiters have a lot of mass to start with. So it's quite hard to completely remove or completely strip a giant planet. So hot Jupiters are safe. However, for these sub-Neptunes, they are strongly affected by this process. And this is, again, for the two reasons. The mass loss rates are much more efficient for these sub-Neptunes, and they have a lot less hydrogen and helium to start with. So you can significantly sculpt. Excuse me. So while giant planets and hot Jupiters are going to be losing mass through atmospheric escape, and it'd be nice to characterize this observationally, the things that are going to be really affected are these sub-Neptunes in the case of hydrogen and helium-dominated planets. The other thing I want to sort of emphasize is that when we are thinking about comparing our atmospheric escape models to direct observational traces of this, the outflows are 3D. And this is a really, really hard numerical problem. So I think still currently there are more observed exoplanets for which we know they are undergoing atmospheric escape than there are 3D simulations. And most of the 3D simulations, again, for numerical reasons, are not for real planets. We kind of sort of make them extra puffy to help our numerical simulations a lot. So the kind of structure you get in pure hydrodynamic outflows is sort of somewhat reasonably well established from these simulations now. So the star is sort of sitting over here somewhere. It's irradiating the planet. It drives this outflow off the day side of the planet, which then sort of wraps around behind the night side, and you get sort of nice Kelvin-Helmholtz-like instabilities. If you then look on the larger scales, then these simulations sort of start interacting with the circumstellar environment. So this is some nice recent work by John McCann, and he's here and he has a poster on some even newer simulations that he promises are for realistic planets, not super puffy planets. So I encourage you to check that out. So when we're thinking about comparing our simulations to sort of direct observational traces of atmospheric escape, we're going to need to sort of think about this 3D structure, and we're going to need to try and put some effort into pushing our numerical models further and trying to actually finally get to the point where there are more models than observations. So I'm going to sort of briefly cover this because some of the other speakers are going to talk more about interpreting observations of atmospheric escape. At the moment, there are sort of two good traces of atmospheric escape. There's a Lyman alpha transit. So this is where you do a transit style observation, but instead of doing it in a broad band, you do it in a narrow line that has a strong sensitivity to material you might find in the outflow. So the Lyman alpha has a strong opacity to neutral hydrogen. So what you can see, this is the Lyman alpha profile. Unfortunately, this center of the line is completely obscured by interstellar absorption, so we don't know what's going on here. We can only look what's going on in the wings. So the black line is what the Lyman alpha from the star looks like when the planet is behind the star. And you can see as the planet comes into transit, you get huge drops in flux. This is a 50% drop in flux. So if you remember what a transit observation means, you're obscuring some fraction of the stellar surface. Right? So in this case, the Lyman alpha is obscuring 50% of the star's surface. Right? Remember, in broadband optical, a planet typically blocks only sort of less than 1%. So this is a huge blocking. And you actually know this is atmospheric escape because a 50% transit radius would imply this material that is temporally associated, so it's going round with the planet, but it's not bound to the planet. It's outside the planet's rotation. So the interpretation is something like this, that you have some escaping cloud that is obscuring some enormous fraction of the star. And it's highly asymmetric in the transit profile due to these 3D natures of these flows. The really exciting one is these recent helium detections, helium metastable line. I'm not going to talk about this because Antonia has an entire talk on this topic later in this session. But this is super exciting because it can be done at high spectral resolution. And as we learned from Jane earlier in the week, high spectral resolution is really useful for getting kinematic information. So I've talked a little bit now about the basics of thermal escape, the basic physics of hydrogen-helium-dominated thermal escape, and now I'm going to talk about how it affects the population of exoplanets. And there is a poster on this topic by Edwin Kite, so I encourage you to go look at that as well. So here's my cartoony picture of what's going on. You have a star which has some planets which all have hydrogen-helium atmospheres when they're born. So it's a solid core surrounded by a hydrogen-helium atmosphere. And I'm going to let this system evolve under the influence of atmospheric escape. So you can see that all the planets at young times, basically most of them sit up here at quite large radii, sort of 5 to 10 Earth radii. These are not giant planets. These are sort of typical sub-Neptunes that have 5 to 10 Earth masses with 10% hydrogen-helium, say. So they have very large radiuses at early times. So for the handful of planets that we can get constraints on their properties at early times, it's really crucial to testing these kind of models as well. Are planets really 5 to 10 Earth, low-mass planets really 5 to 10 Earth radii at young ages? Now I'm going to let this system evolve. So the planets start losing their hydrogen-helium. Some planets, in fact, completely lose their hydrogen-helium atmospheres, whereas some planets retain them. And at the end of the simulation, you tend to end up with two types of planets. Planets that completely lose their hydrogen-helium atmospheres, so that they become what we've called stripped cores, or they retain hydrogen-helium. So you typically have two types of planets, these stripped cores, or planets that have roughly about 1% hydrogen-helium in their atmospheres at the end of this evolution. And this is planet radius period diagram now has this gap in it. In theory terms, this is called the evaporation valley. So I want to sort of briefly understand why you get this valley. It's actually quite simple to understand. If you think of the mass loss timescale, so this is the instantaneous time it would take you to lose the amount of mass you have in your atmosphere. It's basically your atmosphere divided by your instantaneous mass loss rate as a function of your envelope mass fraction. Then in that simple energy limited argument, so this is a perfect place where you can use that simple energy limited argument, what sets your mass loss rate is how much of the star's flux you can absorb. Right? So at very, very low envelope mass fractions or atmosphere masses, the radius of the planet is completely set by the radius of this solid core. Right, so as I add more and more atmosphere, it doesn't change the radius of the planet a great deal. So it doesn't change the flux I absorb from the star a great deal. The atmosphere has negligible mass to the planet's mass, so I haven't changed the mass loss rate. So the mass loss rate must increase as I increase my envelope mass fraction for small envelope mass fractions. Then I'm going to get to the point where the atmosphere is so big, now it dominates the radius of the planet. And what sets how this mass loss rate timescale evolves is how big the atmosphere expands as I add mass. And it turns out the microphysics of hydrogen-helium atmospheres means that the atmospheres expand so rapidly that they absorb so much more flux that the mass loss rate goes through the roof and the mass loss rate timescale comes back down. So I have something that looks like this, with a peak approximately where the atmosphere or the envelope doubles the core's radius. So if I have some time now to lose my atmosphere, this is the sort of time my star is bright, then I can get two types of evolutionary pathways. If I start off here, where I have lots of atmosphere mass, and I start losing mass, right? I have my mass loss timescale is less than the time I have to lose mass. I'm going to start pushing up this curve. So I'm going to start losing mass, but I'm going to get to the point where the mass loss timescale for my current planet structure now exceeds the amount of time I have to lose mass, and my planet becomes stable. So you can see that in these tracks here. You start losing mass, and then the atmosphere becomes stable, and you stay there. But if I start on the other side, here, I start losing mass, my mass loss timescale gets shorter and shorter and shorter, and I just enter a runaway. So you see that you actually, and it's set by basically the stability point is where you have an atmosphere that doubles the core's radius, that this is where the transition takes place. So we have a model, and this is one of the few times where the sort of theory has been slightly ahead of the observations. We had a model, and we now have observations that by eye look in pretty good agreement with the observations. So if you look at it in a bit more detail, you find that the peaks are separated by this factor of 2 in radius. So we have a very, very good, simple physical understanding of why they should be separated by a factor of 2 in radius. These are the stripped cores, and these are the planets with atmospheres that double the core's radius that are maximally stable, those that have the longest mass loss timescales. If you look at just planets that have their properties measured from astroseismology, so this is where you use basically the oscillations of the star to get incredibly precise stellar parameters. So in turn, you can get incredibly precise planetary parameters. So you can measure the stars, the planet's radius, down to something like 1 or 2%. Then you can see that this gap sort of sticks out like a sore thumb now. And you can actually measure the slope here. And what the slope is saying is that at long periods, I have low fluxes. So the only planets I can strip are those with low masses. Whereas I go to higher and higher fluxes, I can strip higher and higher mass cores. So the valley should increase in radius. And this is a great test. Just seeing that slope is a great test that what's going on is driven by this evaporation process. But you can also compare it to detailed models. So this is the slope you would expect if you had constant efficiency, energy limited mass loss. This is the observed slope, so you can see they're clearly inconsistent. However, if you use the slightly more sophisticated numerical models, which account for this variable efficiency, then they're in agreement with observations. And what's essentially going on here is at lower core radii, lower core masses, you have a less deep potential, so the atmosphere can escape quite quickly, doesn't have time to lose a lot of energy to radiation, whereas for the deep potentials, the high mass cores, the large cores, up here, it takes a while for the gas to actually escape the planet's potential. So it has a lot of time to lose energy due to radius efficiency. So these flows are quite efficient down here, and these flows are fairly inefficient. So constant efficiency mass loss is already ruled out by observations, but when we attempt to do something numerically, it's in rough agreement. But one of the key inclusions, and this is sort of a segue to the next part of the talk about the habitability of M-dwarf, is that the majority of the terrestrial planets we observe in the exoplanets form with a large hydrogen-helium atmosphere. And I know I have some Earth science community here, so I'm going to be explicit by what I mean by large. Large means several percent hydrogen-helium atmospheres by mass, or in bars, several million bars of hydrogen-helium when they were born. So not sort of large when people say Earth had a large hydrogen-helium atmosphere that was 10 or 100 bars. This is sort of several thousand times larger. So this has really important consequences for habitability. Perhaps if we were having this conference on a moon surrounding a giant planet, I would be even outrageous enough to suggest that planets don't form in a terrestrial-like fashion. They all have to have hydrogen-helium atmospheres. The only terrestrial planets we see are ones that lose them. But we know from the solar system that's not true. So that's a planet formation puzzle. But we also have this habitability issue. So if planets form predominantly with large hydrogen-helium atmospheres, they're not going to be habitable, even if they sit in the habitable zone. So how can we have habitable planets around stars? Well, fortunately, M-dwarfs are incredibly active, so perhaps we can blow off this hydrogen-helium atmosphere and become habitable. So we have this sort of three-phase suggestion about can habitable zone planets around M-dwarfs become terrestrial planets? So can they lose their initial hydrogen-helium atmosphere inventory? Then can they retain their secondary atmosphere? And if they can retain their atmosphere, can they retain water in that atmosphere? So I'm going to focus on the two things that people have actually done work on. This is perhaps the most important part, and there is almost nothing on this. So, and the question you should be asking yourself when I'm going to talk through some of the latest results is habitability around M-dwarfs fine-tuned or not? I'm not going to tell you whether it's fine-tuned or not. I'm going to leave it up to you. So, and one of the key differences is that the evolution of M-dwarfs in terms of their star's evolution is significantly different to a sun-like star. So this is the evolution of a planet's black body temperature, basically in an Earth-like orbit at the Earth-like age. So this is the stellar track for the sun. So you can see the stellar luminosity increasing. This is the faint young sun problem that Colin was talking about yesterday. But if you go to a lower mass star, then it has a completely different track. It's not a faint young sun problem. It's a sort of inferno young suns problem. But the star is much, much brighter. And if you turn this into what it's doing to the high energy output of these two stars is extremely different. So for the M star here, the 0.4 solar mass star, you can have a flux that's sort of 1,000 times the current Earth's irradiation, even at a gigayear. So this is extreme differences in radiation. So only a factor of sort of roughly more than 2 in stellar mass can make almost sort of 1 or 2 orders of magnitude difference in the total amount of high energy flux you receive over the planet's lifetime. So can you use this extra UV flux to lose your hydrogen helium atmosphere? Well, of course you can, but it depends on how massive you are. So if you're a low mass planet around a 0.4 solar mass star, then you can completely lose your hydrogen helium and become a terrestrial, potentially habitable world quite quickly. If you're a sort of a 0.9 Earth mass star, then it sort of depends. It's initial condition dependent. And if you get to an Earth mass, then you're screwed. The other key issue, right, is, well, perhaps I can lose my hydrogen helium, but can I retain my water? And because of this pre-main sequence evolution of the low mass star, even if I'm in the habitable zone at, say, 4.5 billion years, I'm always going to go through a runaway greenhouse phase, where I'm going to potentially lose water. So this is a nice plot from Luber and Barnes that's showing stellar mass as a function of orbital period. Here are the sort of habitable zone boundaries, optimistic, not optimistic. And this is the time you spend in the runaway greenhouse phase. So for sort of sun-like stars, it's basically a switch, either nothing or all your time. But for lower mass stars, because of this pre-main sequence evolution, they spend a decent fraction, a few hundred million years of their life in a runaway greenhouse effect. So in order to be habitable, you need to be able to retain your water. So these are these are energy limited calculations, constant efficiency calculations for water loss as a function of position in the habitable zone for different masses. So you can see for the sort of sun-like higher mass stars, basically you retain all your water, but for the lower mass stars, you get a quick switch to basically you lose it all. So the solution to this is, well, if I'm going to lose lots of water, but I still want water, I'll just pile a lot more water on to start with. So you can do that, and you can do a bit better. But the outcome of this calculation, and you can keep doing this and keep doing this, but the outcome of this kind of suggestion is that you're either going to be in 2 completely different limits. Either you're just going to be a desert world. You have nothing, or you had so much water to start with that you end up like a complete water world. And there's a poster on this topic by Kevin Moore, which I encourage you to take a look at. So I'm going to talk a little bit more about the physics of water loss and perhaps a possible solution out of this. It's still work in process. So this is my atmosphere. Again, I have my photons coming in, but now I add in some water molecules, and these are going to be dissociated by UV photons. Now I have at some layer in my atmosphere, I have atomic hydrogen and atomic water. And my atomic oxygen is going to start to diffuse up through the atmosphere. Because the oxygen has an atomic mass of 16, whereas the atomic hydrogen has an atomic mass of 1, the oxygen is going to have a slightly smaller scale height. So once I get high up in the atmosphere, oh no, I didn't do anything, I promise.
That shows what happens if you get too high in the atmosphere. Careful.
So I'll continue talking. So obviously the critical process now is I have sort of a mixture of hydrogen and oxygen at the top of the atmosphere. But the oxygen is much more massive than the hydrogen atoms. So the question is the outflow powerful enough to drag the oxygen atoms away, or do the oxygen atoms, are they held there under gravity? And you can work this out. It's quite simple. It's a simple little calculation. And you can calculate the mass of the atom that you can drag along in some outflow. It basically depends on the power of the outflow and the collision cross-section between hydrogen and oxygen. There are also some other limits. So you could also limit your mass loss rate by, obviously, how fast you dissociate the water, and also how fast you diffuse the oxygen through the atmosphere. So both these processes can slow down the water loss, which is a possible way out. The critical thing I want to point out is that this depends on the property of the outflow. It depends on the temperature of the outflow. So we did some very simple calculations for TRAPPIST-1, and basically we assumed the hydrogen-helium properties, assumed the temperatures we get from hydrogen-helium outflows, and calculated how this might affect the water loss. So this is the standard energy-limited loss. But as soon as you start dragging the oxygen atoms with you, which is what's happening in these gray lines, they weigh much more, so you need to use more of your energy to get those oxygen atoms out of your potential, you lower the total loss rate. So it looks like, in these calculations, TRAPPIST-1 is kind of in these limits, the TRAPPIST-1 planet. But we did something, I did this calculation, so I can say this, we did something fairly stupid, which was that we used the temperature that came from the hydrogen-helium dominated outflows. And as an astronomer, I know that oxygen is a ridiculously powerful coolant. So these are sort of beautiful images of star-forming clusters. This is the kind of thing I did on my PhD. They're about 3 to 10,000 Kelvin, roughly what these atmospheres temperatures are. And when you look at these false color images, these are not real images, right? Some of the colors in here, and I think it's blue, is an oxygen cooling line. Oxygen is a very powerful coolant at high temperatures, even in solar metallicity gas. So if you're thinking about increasing the oxygen abundance by several thousand, then it's going to be really important. So the question that I'm suggesting that we're working on now is, does oxygen act as a brake to water loss? So as you increase the flux, you're going to increase the temperature. So that's going to mean you're going to increase the mass that you can drag, and you can start to drag oxygen with you. If you start dragging oxygen with you, it's going to start to cool the flow. That's going to reduce this crossover mass, and you're going to start not being able to drag the oxygen with you. So, and then you're going to increase the temperature again. So do you get some sort of stable limit? So is this sort of bifurcation between desert worlds and Kevin Costner worlds what we're really suggesting for these M-dwarf planets? Or can we end up with something more in between? So this is work in progress that needs to be done. So atmospheric loss from terrestrial planets and secondary element-dominated planets. And this is the key question we should be asking ourselves as a field, especially for M-dwarf habitable zone planets. Key targets for upcoming missions is, can highly irradiated terrestrial planets retain an atmosphere? Or are we just wasting our time? So I'm going to end on a suggestion, and this is something we're working on, is that perhaps we have these two separate pathways to forming a terrestrial planet. We have what I'm calling born terrestrial planets, so planets that form somewhat like solar system planets. They didn't form fully before the gas disk dispersed, so they didn't end up with large hydrogen-helium atmospheres. Or we have terrestrial planets that formed by a stripping of large hydrogen-helium atmospheres. So obviously the atmospheres we're going to get is going to be some sort of balance between resupply and loss. So is the answer we're going to get going to be dependent on these two different evolutionary pathways? Are there going to be two distinct, separate types of terrestrial planet atmospheres that point to their formation mechanisms, or is it more of a continuum? And this is a key theoretical problem and observational problem, right, that we need to focus. Do the observations give us this clarification? And this is something we're working on now. And I'm out of time, so I'm going to skip what I think perhaps a sort of way to get at these, which is loss from highly irradiated rocky planets. They're so hot, you melt their surface and they escape. We can observe them, so perhaps this is a good way to test our secondary atmosphere loss mechanisms. But I don't quite have time to go through all these slides, so I'll finish there and take questions. Thanks very much.
Thank you very much. We have time for plenty of questions. Please state your name and affiliation for this.
Jeremy Lecomte, CNRS. So I was intrigued by the fact that when we look at these stripped cores from Kepler, so of course it means that even the stripped cores start with a big hydrogen atmosphere, but then this is for Kepler targets, so it means for FJK stars basically. So you kind of imply that for M-dwarfs, the mechanism, the formation mechanism would be the same, but at least I feel that around M-dwarfs the disks should be less massive, or at least comparably the planets are further away from the star comparably to size of the mass of the star. So do you have evidence to support that they should be born with a lot of hydrogen helium?
So there is evidence. So you're right, the Kepler data is dominated by FGK stars. There are some few M stars, and this whole feature, so Yan-Chin Wu has a nice paper from 2018 where she shows this whole feature extends down into the M-dwarfs. I'll also make a comment about your feeling. You're feeling that the gas disks and dust disks are less massive around M-dwarfs, which is an empirical fact, right? But if you look at the mass contained in the exoplanet population, it's actually more massive around the lower mass stars. And there's more of them. So that's an intriguing question. So at the moment, given the observed data we have, there is no evidence apart from the terrestrial planets in our solar system that planets form without large hydrogen helium atmospheres, which I think is fairly shocking.
Right, yes, in the front.
So how well defined is the core envelope boundary for these sub-Neptunes, given what we're learning about fuzzy cores for Jupiter?
So that is an excellent question. It's a question to which I can answer with a feeling. So one of the things that we know about this hydrogen helium loss is that the radiative cooling is at sort of slightly supersolar metallicities is dominated by the metals. So if you do have a fuzzy core boundary where you start getting into a hydrogen helium atmosphere that is increasing in metals, the mass loss rate is going to drop like a stone, right? So when I say they're stripped cores, right, they're stripped in the sense that we have no radius evidence for a large hydrogen helium atmosphere. So it may turn out when we start looking at these super Earths, and it's part of that suggestion in these terrestrial planet pathways, that they do retain a thin veneer of hydrogen helium. And that could be coming from this fuzzy core aspect. But it's not. It can't be a very extended fuzzy core, otherwise you wouldn't be able to get this process. If it was, then we're just wrong.
Thank you. Any more?
Yeah, one there and one there.
Would a magnetic field help this planet to do your calculation, take that into account?
Yeah, so someone always asks me this question. So I always bring a slide. So yes. So magnetic fields suppress mass loss for hydrodynamic driven mass loss. And they do it because you have these outflows are strongly ionized, so they're coupled to the magnetic fields. Ideal MHD is a very good approximation. So you get closed field lines close to the equator. This is where most of the energy is deposited. So you only get inefficient flow along the poles. So this significantly reduces the mass loss rate by about an order of magnitude. So you can play this whole game again with this process and compare to the radius gap data. So if you do that, as you increase the field strength, you still get the same process. You just need to compensate for the reduced mass loss rates by reducing the mass of the planets you're losing mass for. So instead of favoring rocky cores with basically zero fields, we favor icy cores with strong fields. The fact that the 10 or so planets down here that have measured masses are all consistent with Earth-like rock perhaps points to me to suggest that these things don't have 10 Gauss fields or 1 Gauss fields. And I mean here the field strength at the top of the hydrogen-helium atmosphere, you double the core strength. So if you have a 1 Gauss Earth-like field, it's going to be 0.1 Gauss by the time you get to the top of the hydrogen-helium atmosphere. So it doesn't matter. So to make this work, you need dynamo-generated fields in sub-Neptune, something we don't have in the solar system, so we have no idea what it does. But at least it's saying to me they don't generate a few Gauss fields.
The mass loss rate by diffusion limited process, is that not relevant here? Because you've considered only the energy limited escape. Yeah,
so I did point out that you can slow these processes down, especially for the water loss, by either limits due to just dissociating the water or diffusing the hydrogen through a very oxygen-rich atmosphere. And that does slow down the mass loss rates. In those Luger and Barnes calculations I considered, they also considered the diffusion limit, and they argued for their calculations based on their temperature structure, right, which is based on not including oxygen cooling. They argued that energy limited was more applicable. But when the calculation is done properly, that may not be true. And the diffusion limit may be another way to save our water on our M-dwarf habitable planet.
Thank you. Let's thank Owen.